Hello everyone. Welcome to the live problem solving session for the course Introduction to Galois Theory. So we are in week 5 now. So I have to solve some problems related to the content of week 5. So before that, it's better to recall the topics of this week. So let me give you a brief sketch of the contents of this. So in the previous week, we have already done uh, Galois extensions and several characterizations of Galois extensions and the main theorem of Galois theory, which we call as fundamental theorem of Galois theory. And after that, we have done some consequences of that fundamental theorem. And in this week also, we will continue with some consequences of the fundamental theorem. So, what we have proved is uh, if we have a finite extension, let's say K over F be a finite extension of fields, then we can say that it has only finitely many intermediate fields. So there is a theorem related to this statement is there, which is known as primitive element theorem. So we will see the exact statement in the uh, I think in the last lecture of this course. But what we have done here mm, is the following. So if we have a finite separable extension, so a finite separable extension has only finitely many intermediate fields. And the proof of this statement is also fairly easy. So as we know that a finite Galois extension has only finitely many intermediate fields because the Galois group has only finitely many subgroups by the fundamental theorem, right? So this finite separable extension, we can extend it to a Galois extension, let's say L over F. So then we have a tower like this. And since this L over F is Galois, it has only finitely many intermediate fields. So this extension K over F, this also has finitely many intermediate fields. So we just extend this separable extension to a finite Galois extension. And we can take the Galois closure also. So that's the idea. And we have also seen one example that if we remove this condition, that separability of this extension, then this statement may not hold. So we have seen an example of a finite field extension. uh, Finite extension with a finite extension with infinitely many intermediate fields. So basically we have to construct a field which is non-separable. So that we have already done. And after this we have defined primitive extensions and also primitive elements. So we will see more about primitive extensions and primitive elements in the last lecture. So I will not talk about that thing here much. And then we have defined Kumar extensions. So basically for that we need to define primitive roots of unities. So that is also we have done. And in the end of this week, we have characterized Kumar extensions as cyclic extensions. So to prove this, we need to prove two theorems. So we have already stated those theorems, and we will give the proof in the next week. So basically in the week 6. So these are the rough topics of this week. Okay, so now maybe we can solve some problems. Okay, so let me write down the problem first. So let K be the field. So it is the field of all rational functions. So let K be the field of all rational functions over C, or be the rational function field. And let omega be the primitive cube root of unity. So we already know that this is basically e power 2 pi I by 3. So be a primitive cube root of unity in the complex field, or field of complex numbers. So now we will define some automorphisms of this field K. So we have already seen that how the Galois group, so how the Galois group of this rational function field looks like. That we have already done in the, I think in the first or second live session. So now let's write down two more automorphisms from that Galois group. So define sigma and tau from K to itself by sigma of t is equals to omega t, and tau of t is 1 by t. So to define an automorphism, C automorphism of K, we just need to mention the image of this variable t. That's all. So define this. Now, now let G be the group generated by these two automorphisms. Then show that the first thing is this group is isomorphic to basically D3, or which is same as S3, and the second one is we need to find the fixed field of this group. So the fixed field of this group is same as C adjoint uh, TQ plus 1 by, or I should write T power minus Q. Okay, so these two things we have to prove. So the problem is fairly easier. Uh, uh, so let's see how to do this. So what we have is, we have this field CT and we have two automorphisms. So we need to find this group generated by these two automorphisms, and we need to find the fixed field. So we have only two tasks. So let's do one by one. So we have already done one problem of this similar type, but let's do it also, because I feel that this type of problems are not easier to handle. So first we will prove that this group defined generated by sigma and tau, this is isomorphic to D3. So how to prove that this is isomorphic to D3? So what we know about D3 is D3 is a group of order 6, and not only that, it is also non-abelian. So more specifically, there are only two groups of order 6 up to isomorphism. One is cyclic and one is non-abelian, and the non-abelian is D3. So to prove G is isomorphic to D3, we have to prove that cardinality of G is 6 and G is non-abelian. Right? So that is the one way. So first let's prove that cardinality of G is 6. So observe that. So we need to find the order of G. So first let's try to find the order of these two automorphisms, sigma and tau. So observe that sigma squared t is basically sigma of omega t, and this is same as omega times sigma of t, because sigma is a C automorphism. So this is omega squared t, right? So this is not equals to t. So this will imply sigma square is not identity on k. So what is sigma q now? So sigma qt is basically sigma of omega square t, and again it is same as omega square sigma t. So it is omega q times t, but omega is a primitive cube root of unity, so it is same as t. So sigma q maps t to t, so sigma will fix all element of k also. So this will imply sigma q is basically identity on k, and this will imply order of sigma is 3. Now what is order of tau? So if we take tau square of t, so it is same as tau of so what is tau of t? So it is 1 by t. So it is basically T inverse, but tau is a automorphism. So it particular it is a group automorphism on the group of multiplicative on the multiplicative group. So this is same as tau t whole inverse, and again it is same as T inverse of T inverse. So this is same as T, and this will imply tau square is basically identity on K. So order of tau should be 2. Right. So we have found the order of sigma, which is 3, and also order of tau, which is 2. Now if we calculate sigma tau of t, what we will get? So this is basically sigma tau sigma of t inverse, and this is same as sigma tau sigma of t whole inverse we can take, because all are automorphisms. So this is same as sigma tau omega t and inverse of that. Now this is same as sigma of omega tau t. And whole inverse. Now this is same as sigma of omega t inverse and whole inverse. So this is same as omega sigma t inverse of this and whole inverse. Now what is this? So this is omega inverse, and sigma t is basically omega t and inverse of this. So this is same as, so what is inverse of omega? That is omega square. And this is T inverse omega inverse. Am I doing correct, or I have made a mistake. So I need to switch the elements. So now it will be sigma t times omega inverse, right? Because a b whole inverse is same as b inverse a inverse. So that is what we are using. Now this is same as omega t times omega square. But I think okay, let us check this again. So maybe we can compute it directly also. So let's not involve inverse here. So what we will do is, it is just uh, sigma tau and omega inverse tau inverse. This is same as we can take omega inverse out. So sigma tau t inverse. So this is omega square. This is sigma, and this is again inverse tau of t inverse. So it will be just t, and this is same as omega square omega t. So this is omega qt, and this is same as t. So this means sigma t is basically identity on k. So from this we will get uh, tau sigma is same as sigma inverse tau. So so basically what we are getting, so this will imply the group G, which is generated by sigma and tau, will be same as identity on k sigma square, because sigma q is identity. Now tau sigma and tau sigma square. So this will be all elements of this group, and we have this relation. So this will clearly imply this is isomorphic to D3. These are the generators, and this is the relation, right? So we write D3 as uh, sigma q is identity, which is same as tau square, and tau sigma is sigma inverse tau. So we usually write in this way, or maybe so the first part is done. So the group generated by these two automorphisms is basically S3. Now we need to find the fixed field of this group. So we want to show that this fixed field is same as C adjoint TQ plus T to the power minus 3. So what we will do is we will prove that both side inclusions. Kg contains this, and Kg is also subset of this. So that is the usual way. So one inclusion is trivial. So note that. So what is image of TQ plus T power minus Q under sigma? So this is same as sigma TQ plus sigma T whole power minus 3. So this is same as omega TQ plus omega T whole power minus 3. So if we split again, we will see that it is same as TQ plus T power minus 3. Right? So this means this element is fixed under sigma. And what is the image of this under tau? So again, you can see that it is same as tau t power 3 and tau t power minus 3. So this will be t power minus 3 and this will be t power 3. So this element also fixed under tau. So this implies tq plus t power minus 3 is fixed under sigma and tau. So this will imply this element is fixed under the whole group, because the group is generated by sigma and tau. Now this is fixed, so this will imply this field is also fixed. This is subset of Kg, right? So because this field is generated by this element. Now so what we have now? So We have k here, which is c adjoint t, and we have kg here, and we have c adjoint tq plus t power minus 3. So we need to prove that kg, these two are equal. That we have to prove. So how we can do that? So there are multiple ways of doing this. So in the lecture we have done in one way. So I want to give you one more way of doing this thing. Okay, so okay. So claim is we have to prove this equality. Claim is kg is subset of c adjoint tq plus t adjoint minus 3. So let's see by a fairly easier method. Now observe that k over kg, this extension is Galois, and this degree is same as cardinality of g, which is 6, right? So k over kg is Galois, and this degree of this extension is cardinality of group, which is 6. So this is by the earlier theorem that we have done uh, while we were doing the fixed fields. So this will imply T is algebraic over kg, right? Because k is basically c adjoint t. So this extension is finite, means it is algebraic also. So what is the irreducible polynomial of t over kg? So we already know the Galois group. So we need to find the irreducible polynomial. So by using the Galois group, we already know how to find the irreducible polynomial. So let's find the irreducible polynomial of t over kg. So for that we just need to look the orbit of t under the action of g. So for that we need to uh, look at the orbit of t under the action of g. So basically, so to find the irreducible polynomial of t, we just need to find the all other roots of the irreducible polynomial of t in k, right? Then we can write down the polynomial easily. So we need to find basically the conjugates of t in k. So the irreducible polynomial of t over kg is basically some x minus t x. So what is our group g? G is basically 1 sigma square tau tau sigma square. So we need to take image of t under all elements. So this is sigma t. Now this is sigma t square. Now this is x minus tau t. This is x minus tau sigma t. And this is x minus tau sigma square t. Right? So this image of t under all these elements will give us the conjugates, give us the other roots of the irreducible polynomial. And we are just attaching all the roots. so that we can get the irreducible polynomial. Now what is this? So this is same as x minus t, x minus omega t, x minus omega square t square, x minus t inverse, x minus omega inverse t inverse, and finally x minus omega power minus 2 t inverse. Now let's rewrite this. So this is same as x minus t, x minus omega t. The first three will be unchanged. X minus omega square t square. But this is x minus t inverse, x minus, so this is omega square t inverse. So I will just write interchange these two. Omega. So this term will be omega t inverse. So I will write down that one first. And this term will be omega square t inverse. So if we club these three together and these three together, what we will get? So it's just multiplication. You can check it. So it will be just xq minus tq, and this portion will be xq minus t power minus 3. And if we multiply these two, we will get x power 6 plus xq times tq plus t power minus 3 plus 1. So this is the irreducible polynomial of t over kg. But this coefficient is belongs to this field, right? So this is belongs to C adjoint tq plus t minus 3. So this will imply t is algebraic over this field also, because t satisfies this polynomial which belongs to this. Not only that, the degree, so degree of k over C adjoint tq plus t power minus 3, which is same as degree of C adjoint t tq t minus 3. This is same as degree of irreducible polynomial of t over C adjoint tq plus t power minus 3. But this satisfies this polynomial which has degree 6. So it has to be less than degree 6. So what is the picture now? So here we have k, here we have kg, here we have C adjoint tq plus t minus 3. So this is 6 and this is also less than 6. So these two has to be equal. So what I am telling is, so this implies we have k over kg which is 6, and this is bigger equals to, sorry, less equals to. So this is less equals to k over kg times k over f, sorry, kg over f, right? And this is same as k over f, but because the degree is multiplicative, and this is less than 6. So this will imply k over kg is same as k over f, and this is 6. So we have kg over f must be 1. So this will imply f must be kg. So this has to be 1 because we have already one containment. Sorry, not. So okay, so let me make this one f. Okay, so we have proved that the fixed field is C adjoint TQ plus T power minus 3. So this we have found by finding the irreducible polynomial. So this is one method. So this is a systematic method for finding the irreducible polynomial. But you can find the irreducible polynomial by just observing, right? Let me give that as method 2. So observe that T satisfies xq plus, sorry, x power minus 3 minus tq plus t power minus 3, this equation, right? And this is, so this will imply, so if you multiply this equation by xq, so t satisfies the polynomial x power 6 plus xq times tq plus t power minus 3 plus 1, and this is belongs to C adjoint tq plus t power minus 3. So t has to be algebraic over this field and degree of t has to be less equals to 6. So this is by just directly observing this equation because t satisfies this equation. This is one other method. So this will imply this has to be less equals to 6. So we are not using the Galois group to finding the irreducible polynomial in this method. So we are just using observation. Now what is the third method? So in the third method, we can directly find this degree of this extension. So this I have given as an exercise in the earlier live sessions. So there is a formula for this. So tq plus t power minus 3 is basically t power 6 plus 1 by tq, right? So this degree is same as maximum of degree of the numerator comma degree of the denominator. So degree of t power 6 plus 1 comma degree of t cube, and this is basically 6. So this is the formula for finding. So I will write down the formula here more specifically. So I have already done this. So C adjoint T and C adjoint, let's say PT by QT. So degree of this is same as maximum of degree of PT comma degree of QT. So we can use this formula directly. So once, so we have found this degree here specifically equals to 6, and here it is less equals to 6. So in all three cases, means in all three ways, the answer is same, that the fixed field has to be C adjoint TQ plus T power minus 3. So this completes the proof. Okay, so now let's move on and do some other problems. So this is problem number 2. So let P be an odd prime number, and let fx be the polynomial x power p minus 2 belongs to q of x. So I think we have already discussed about the uh, so if we consider the splitting field of this polynomial over q, so we have already discussed about that extension, that is Galois, and what will be the degree of that extension and how that extension will be look like. But I want to give the description of the Galois group of that extension. So the problem is, so that the Galois group of this polynomial, Galois group of f over q is isomorphic to the group defined by, so here we have A, the group of matrices of order 2 by 2, where these entries A, B are coming from the finite field of P elements, and A is non-zero. So this is a particular group. We need to prove that the Galois group of F over Q is isomorphic to this G. So Galois group of F over Q means you take the splitting field of F over Q, let's say that is K, and look at the extension K over Q. And Galois group of this extension is the Galois group of F over Q. So that is the terminology. So how to prove this? So first let's recall the things that we already know. So let K be the splitting field of F over Q, right? Then we know that K is basically same as Q adjoint, the real pth root of 2 and the primitive pth root of 1, right? This is the notation. So where uh, zeta p is a primitive pth root of unity in C. A primitive pth root of unity in C. So this is the splitting field of x power of this polynomial x power p minus 2 over q, right? So this thing we have already done in the lectures. And we also know the degree of this extension, and we also know this degree is same as p times p minus 1, right? So how we have done this? We have done this because of this tower. So here we can take q adjoint p root of 2, and here we can take q adjoint zeta p, and here we have q. So we have this tower. So this is simply p because it satisfies x power p minus 2, which is irreducible by the Eisenstein's criterion. So this is p. This is phi of p, the Euler phi function. So this is p minus 1 because this is the cyclotomic extension. And this one is p because as the same reason as this one, and this is p minus 1. So now you use the multiplicativeness of the degree. So then you will get that this degree is p times p minus 1. So these facts we already know. Now we want to find the Galois group is specifically isomorphic to this group. So you can verify that this group has also cardinality p times p minus 1, right? Because this A is non-zero, means we have p minus 1 choices, and B can be any one element of Fp. So B has p choices. So here we have p minus 1 choice, here we have p choice. So in total we have p times p minus 1 choice. So total p times p minus 1 elements. So now how to prove that the Galois group is basically isomorphic to this group? So so let's write down the roots of this polynomial. So we also know that. So now the roots of x power p minus 2 in k are basically the real pth root of 2 zeta p times pth root of 2. Okay, I will write the other way around. So real pth root of 2 times zeta p, real pth root of 2 times zeta p square, and so on, real pth root of 2 times zeta p power uh, p minus 1, right? So these are the all roots. So so now observe that. So we want to prove Galois group of k over q is isomorphic to G. So we need to give a specific isomorphism. So we need to define a specific map, right? So how to do that? So first observe that if sigma belongs to Galois group of k over q, then what is the image of pth root of 2 under sigma? So image of this can be any other roots of this polynomial, right? Basically the conjugates of this element. So we have these p choices. So this is basically pth root of 2 times some zeta p power I sigma, right? Where I sigma can run from 0 to p minus 1. So it will be depend on sigma. This index will be depend on sigma. That's why I am writing I sigma. So image of k root of 2 can be any other root of this polynomial. And what will be the image of zeta p? So image of zeta p can be any other root of the irreducible polynomial of zeta p, right? So what is that? So that is basically zeta p minus x power p minus 1. So basically the nth cyclotomic polynomial, it's cyclotomic polynomial. Or more specifically, image of this can be any other primitive pth root of unity. And what is that? Sorry, any other pth root of unity. Need not be primitive. Just just pth root of unity. So that is basically zeta p power some j of sigma, where 1 less equals to j of sigma less equals to p minus 1, right? So why we are looking image of these two elements? Because k is basically q adjoint real pth root of 2 and zeta p. So any q automorphism can be described by just the image of these two elements. We just need to describe image of these two elements to get a q automorphism. Now using image of this, we will define a map from the Galois group to G. So this part is important. So let me mark this as star. Okay. Now uh, define, let's say, how to write it. Okay, let's say phi from this Galois group of k over q to G by just phi of sigma, image of an automorphism, should be a element of the matrix G, right? So first will be j of sigma, and second entry will be I of sigma, and it is 0 and it is 1. So j of sigma is running between 1 to p minus 1. It cannot be 0. So I am putting this as the first entry. And I of sigma can be any of 0 to p minus 1. So I am putting this in the second entry. Now we claim that phi is a group isomorphism. So claim is it is phi is a group isomorphism, right? So we have defined a function, we need to prove that it is a group isomorphism. So we need to check several things. First of all, it is well defined. So let's do the proof of this. So first one is phi is well defined. So to check well definedness, we need to check that these things are specifically depend on the sigma, and this element is belongs to G, right? But that is clear from the star. So this follows from star. Because this element clearly belongs to G. So that is enough to check the well definedness. And this is guaranteed from this star. So well definedness is just to convince yourself that it is well defined. Now I is a group homomorphism. So we need to prove that phi is a group homomorphism. So this is just a routine check, but let me do this because it's not it will not take that much time. So once you have defined this map, and once you have observed this fact in the star, the all other things will follow just routine. Okay, so let sigma and tau be two elements from the Galois group, and we want to show uh, phi of sigma tau is exactly equals to phi of sigma times phi of tau. Then only it will be a group homomorphism. So let's find out both LHS and RHS that they are equal or not. Now what is phi of sigma tau? So according to our definition, it is j of sigma tau, I of sigma tau, 0, 1. But what is this j of sigma tau and I of sigma tau? So for that, we need to look at the image of pth root of 2 and zeta p. So I will write here. So sigma tau of pth root of 2 is basically sigma of pth root of 2 zeta p times I sigma, means I tau. Now this is same as uh, sigma of pth root of 2 times sigma of zeta p power I tau. Right, now this is same as pth root of 2 zeta p times I sigma, and now this part is zeta p times j sigma whole power I tau. So this is pth root of 2. So this is pth root of 2 times zeta p times I sigma plus j sigma times I tau. So we have found the one image. So yeah. So we have found j sigma tau. Sorry, what I sigma, and the other. Let's find the other image. So sigma tau of zeta p. So this is same as sigma of. So what will be image? It is just j of sigma. So zeta p j of tau, and this is same as, you can see, zeta p times uh, j of sigma times j of tau, right? So here we will get j of sigma times j of tau, and the second entry is this one. So this is I of sigma plus j of sigma times I of tau, and this is 0, this is 1. So we have computed the LHS. Now we also know the RHS. So let's write down here. So we need to find this product phi of sigma times phi of tau. So this is j of sigma I of sigma 0 1 by the definition times j of tau I of tau 0 1. Now let's find the product. Just usual matrix multiplication. So it is j of sigma times j of tau, and this is j of sigma I of tau plus I of sigma, and this is 0, this is 1. Now let's check. So here we have I sigma plus j sigma times I tau. Yeah, it is exactly same. So this is exactly same as phi of sigma tau. So phi is a group homomorphism. One just need to do the calculations carefully. That's all. So we have proved that this map is a group homomorphism. Now we need to prove that. Uh, so we want to prove that it is an isomorphism. So we need to prove that it is a bijection. But so how to prove that it is a bijection? So the third step, phi is a bijection. Right? So how to prove this? So note that cardinality of the Galois group, this is same as this degree of this extension, which is p times p minus 1, and cardinality of the group is also p times p minus 1. Right? So both these sets, this one and this one, has same cardinality. So if it is 1 1, so it will be bijection if and only if it is injection, if and only if it is surjection. So proving either injectiveness or surjectiveness is enough. So to prove phi is bijective, it is enough to prove that phi is injective. Right? So we will prove phi is injective. So since phi is a group homomorphism, uh, we will prove that its kernel, it's just the identity subgroup. So now, what is the kernel? So kernel of phi is basically all those automorphisms of the Galois group whose image under phi is the identity matrix. Right? So this will imply it is sigma belongs to the Galois group such that j sigma I sigma 0 1 is 1 0 0 1, and that implies sigma, all those automorphism sigma of the Galois group such that, so let's compare component wise these two matrices such that uh, j sigma is 1 and I sigma is 0, right? And more specifically, it is the set of all those automorphisms such that sigma of pth root of 2 times sorry, just pth root of 2. So did I write? Yeah, it's fine. It will be pth root of 2 times zeta p power j sigma, which is 1. Sorry, which is 0, I sigma. So this is 0. This is, that means it is just p root of 2. And image of zeta p will be zeta p power j sigma, which is 1. So okay, just let me write 1. Okay, just let's put this thing. So it is, so image of both these elements are same, so it should be the identity. So this has to be identity on K. So kernel is identity, so this will imply phi is injective. So we have proved that phi is bijective also. So this phi has to be a group isomorphism. So hence phi is a group isomorphism. And this completes the proof. So we have proved that the Galois group of x power p minus 2 is basically this matrix group. Okay, then maybe now we can do some problems on finite fields, because in the course we have not done much problem on finite fields, so it's better to do some problems. Yeah, so it's problem number 3. Okay, so let f be a finite field of characteristic p. So p has to be a prime number. Then show that product of all non-zero elements, of f is basically so it is plus 1 if p equals to 2, and it is minus 1 if p not equals to 2. So f is a finite field, means it has a finitely many elements, and its characteristic is a prime number. So if you take the all non-zero elements and take the product, then that has to be either 1 or minus 1. It depends on the characteristic of the field. Okay, so let's solve this. So if you recall that cardinality of finite field is just power of the prime characteristic. So now cardinality of f is basically some p power n. So for some n greater equals to 1. right? So this is a very basic fact. So maybe you can refer to the structure theorem of finite fields that we have recall in the first week, uh, and also recall that uh, the elements of Fn, the elements of F are basically the roots of the polynomial uh, x power p power n minus x belongs to fpx. So you just collect all the roots of this polynomial and you will see that that set forms a field, and that is basically this field f, because this has exactly p power n roots. And if you remove the factor x, so all the non so all the non-zero elements of f are exactly the roots of x power p power n minus 1 minus 1, right? Because we are just taking x common and we are replacing that x, so we are removing the factor x. So thus x power p power n minus 1 is same as product of x power minus a, where a belongs to f cross, right? Where f cross is the set of all non-zero elements. Because this is roots of this are basically the are all the non-zero elements. So we can write this. Now let's put x equals to 0. So in the left hand side we will get minus 1. So minus 1 is basically product of minus a, where a is in f cross. Now what is this? This is same as minus 1 power p power n minus 1 and product of all the non-zero elements. So this will imply product of all the non-zero elements is basically same as minus 1 power p power n, right? Now this will be 1 if p is even, and this is minus 1 if p is not 2, p is odd prime, and this concludes the proof. So we have to just use the structure theorem, one part of the structure theorem, that all the elements are basically roots of this polynomial. All the non-zero elements are roots of this polynomial. So now using this, we can deduce one theorem which is known as Wilson's theorem. So okay, let me state that. So problem 4. So using exercise 3, deduce the following, deduce the Wilson's theorem. Now what Wilson's theorem says? So let me write down the statement. So for a prime number p, p minus 1 factorial is congruent to minus 1 mod p, right? So that means p divides p minus 1 factorial plus 1. So how to prove this? So this is the Wilson's theorem, and we will prove using the previous exercise. So note that if p equals to 2, then p minus 1 factorial is basically 1. So the right hand side is 2 and it is divisible by 2. So p minus 1 factorial congruent to minus 1 mod p. So nothing to prove. So nothing to prove. So let p is not equals to 2. That means p is an odd prime. And in that case, product of all non-zero elements are basically minus 1. So then uh, product of all non-zero elements in Fp, we are not taking Fp power n, just Fp. Fp is minus 1, right? And also we know, so you just take the polynomial x power p minus 1 minus 1. This is same as product of all x minus a, where a belongs to Fp cross, right? But what is this? Fp cross means this is same as x minus 1, x minus 2, dot dot up to so on, x minus p minus 1. Because we know the elements of Fp in particular. Now put x equals to 0. So the left hand side is minus 1 equals to minus 1 power p minus 1 times p minus 1 factorial. So this implies p is an odd prime. So this is just 1. So p minus 1 factorial equals to minus 1. So this will imply p minus 1 factorial congruent to minus 1 mod p. And this proves the Wilson's theorem. So we are not exactly using the previous exercise. We are just using the idea of the previous exercise. So basically the structure theorem of finite fields. Okay, so this was problem number 4. Okay, let's do this. So problem number 5. So let F be the field, F3x quotient by x cube plus 2x plus 1. Okay. So, and also let x be the image of x in x. So that means x is specifically this quotient, which is x cube plus 2x plus 1. So then uh, show that x is a generator of the cyclic group F cross. So what we are doing this? So this is a field and this is a finite field. So its multiplicative group is a cyclic group, and it's a cyclic group of finite order. So we need to prove that this specific element is a generator of the cyclic group. So that is our task. So now how to do this? So how to prove that X is a generator? So, so to prove X is a generator of the cyclic group uh, of the cyclic group F cross, uh, we need to show the we need to show that order of this element X is same as order of this group. So then only X will generate the whole group, right? But what is order of this group F cross? This is same as order of F minus 1. But how to find this order? So, so in particular, F3x modulo x cube plus 2x plus 1. So this is a field. That means this is an irreducible polynomial. So, so this field specifically looks like, so this is degree 3 polynomial. So it will be cx square such that ABC is in F3. So this is the structure of the elements of this field. So here A, B and C coming from F3. So this has 3 choice, this has 3 choice, this has 3 choice. So in total we have 3 power 3 choice. So total 27 elements. So if we remove the 0 element, then it will be 26. So this is 27 minus 1, 26. So we need to prove that order of X is 26. Right? So that is our task. Now how to prove order of X is 26? So we need to prove uh, X power. So order of X is 26 means order of X cannot be less than 26. means x square cannot be 1 and x power 13 cannot be 1. Then x power 26 has to be 1. That means x order of x has to be 26. But these things are just simple calculations. So note that in A we must have x cube plus 2x plus 1 because this polynomial is irreducible. So in this thing x cube plus 2x plus 1 has to be 0. So this is also one theorem known as the Kroneker's theorem or the fundamental theorem of field theory. So it has been done in the rings and fields course. So you can recall it from there or you may refer to any standard book. So this thing has to be 0 in F. So from this, so you can directly compute that these two things cannot hold. So that is just simple calculation. So I am not going to do that. So this is the main idea. So from this, direct calculation will show uh, x power 13 is exactly 2. So it cannot be 1. So that you can verify. So I am leaving this part to you. So just use this equation to prove this fact. So this will imply order of x is 26. So x is a generator of this group. Okay. And so one can also modify this thing to, okay, let me, I will put that as a remark or other question. So show that x is not a generator of the cyclic group uh, which is f3x modulo. So what we have taken x cube plus 2x plus 1 x cube plus 2x plus 2. So instead of 2x plus 1 I will take 2x plus 2. So you take the cyclic group of this and you can check that x is not a generator. This is one part, but 2x is a generator. So using the same idea you can prove this. 2x is a generator. So you may find that either x square is 1 or x power 13 is 1. And for 2x you will see that 2x square is not 1 and 2x power 13 is not 1. So you have to prove this thing using the same idea in the previous exercise. So this is just a computational exercise. So you just try to do this. Okay. So I think I have done sufficient problems for this week. Yeah, maybe we can do more in the next week tutorial. Okay, so it's a good time to stop. So we will again meet in the next week same time.